So we've been looking a lot about expressions that are rational expressions. Now let's go back to functions. Let's look at reciprocal functions. So what do we mean by reciprocal functions? The parent function, which is kind of like the overarching function, which like the parent quadratic function would be x squared. So here the parent reciprocal function would be f of x equals 1 over x. Okay, we call it a reciprocal function because it is the reciprocal of f of x equals x. Okay. In other words, what we're saying is we have an x in the denominator even after we reduce. I'll remind you that f of x equals 1 over x is the same thing as x raised to the negative first power, right? So it's not a polynomial function. Polynomial functions only have positive powers. Okay, let's take a look at what this function looks like on a graph. So on a graph, and this is just a sketch, here's our y-axis, here's our x-axis. On a graph, the reciprocal function looks as follows. Okay. And I can even show that to you. If you go to Desmos, it's a great graphing calculator. And if we look at 1 over x, this is what it looks like. Okay, so the domain here is all x values. It keeps going off to the side to infinity and negative infinity. But over here, we actually never reach 0. Okay, there is no value at x equals 0. It just keeps getting closer and closer and closer, but it never actually reaches x equals 0. So the domain is x such that x is not equal to 0. And if you look at the range, it's similar. Okay, we get closer and closer to 0, our y values, but we never actually reach them. By the same token, the y values do go to negative infinity and infinity. So our range is similar. It's y as long as y is not equal to 0. Okay, and how do we know that this is true? Sorry, I should minimize this. How do we know that this is true? Well, the function is 1 over x. The only way that we could get y equals 0 is if the numerator is 0. Okay, and this is 1 over x. The numerator is 1. Okay, similar to the domain, for the domain, if x equals 0, 1 over x is undefined. So it wouldn't work. Let's take a quick look at 1 over x squared. So 1 over x squared is still a reciprocal function. Okay, if we look at the graph of 1 over x squared, you can see it's similar, but instead of being in opposite quadrants, they're in adjacent quadrants, quadrants that are next to each other. So 1 over x squared looks as follows. It's very similar. Even the domain and the range is similar. Okay, the domain here is still x can't be 0, because if it were 0, then this would be undefined. We would have 1 over 0. And in this one, the range is a little bit different. The range is that y has to be greater than 0. Okay, so y is always positive because x squared is always positive. So what helps us figure out what a reciprocal graph looks like is something called an asymptote. Every reciprocal graph has an asymptote. So what is an asymptote? An asymptote is a line that the curve approaches but never touches. So it's a line. You can see it here. X equals 0 is an asymptote. We get this red curve gets very, very close to x equals 0, but it never touches it. Same thing with y equals 0. The curve gets very, very close to y equals 0, but it never quite touches it. Okay? So vertical asymptotes are not in the domain of the function. And horizontal asymptotes are not in the range. So if we go back here for a second, okay, a vertical asymptote here would be at x equals 0, and a horizontal asymptote would be at y equals 0. Okay, and that's actually true for f of x equals 1 over x squared as well, right? We get really close to x equals 0 and really close to y equals 0, but we never actually touch them. So in this video, we're going to talk about how to find vertical asymptotes. In the next video, we're going to talk about horizontal asymptotes. Okay, so let's say that we're working with f of x equals 1 minus x over x squared plus 7x plus 12. So if we want to find the domain, what we want to look for is where the denominator is not equal to 0. So we can factor the denominator. This factors to x minus 4 times x minus 3. So the domain, so we want x minus 4 times x minus 3 to not equal 0, which means x minus 4 can't equal 0, and x minus 3 can't equal 0. Or x can't equal 4, and x can't equal 3, right? So we're factoring it. So our domain is x as long as x is not equal to 4 and x is not equal to 3. I didn't spend a lot of time on that because you can go back to the video on domain, okay? We're saying our denominator can't equal 0. Figure out where the denominator is equal to 0. That's what's not in the domain. Why is this important? It's important because it's going to tell us where the vertical asymptotes are. So a vertical asymptote exists where our denominator equals 0 except in a certain case. And that's if the factor cancels. If we do have a factor that cancels, then what we have is a hole or a discontinuity in the graph. This is also called a discontinuity. Okay, what do we mean by that? An asymptote would look like this. A hole is literally a hole. Okay, you've seen those with piecewise functions. Okay, so let's find the discontinuities in the holes. We'll do it for 3 functions. Okay. Or really, sorry, the holes in the asymptotes. Okay. Let's say that we have f of x equals x minus 6 over x squared minus 36. Okay. What we want to do is we want to factor the denominator. Okay. Factor everything, really. The denominator is a difference of squares. So it factors to x minus 6 times x plus 6. Okay. The x minus 6 cancels. So this is going to be 1 over x plus 6. Now, how do we find the whole versus the asymptote? Okay. Well, here's what this means. The denominator is 0. At x equals 6 and at x equals negative 6. When the denominator equals 0, you're either going to have a whole or you're going to have a vertical asymptote, okay? These two functions are the same, except the domains are different, okay? So I just want to be clear about that. So they're almost the same. So the fractions, the values are the same, but in one case, you can have x equals 6, and in the other case, you can't. So here, the domain is x such that x is not equal to 6 and x is not equal to negative 6. At x equals 6, there is a whole. How do we know? X equals 6 or x minus 6. Canceled. At x equals negative 6, there is a vertical asymptote. So in sum, to find the wholes in the vertical asymptotes, you factor the denominator. Set each factor equal to 0. There's a vertical asymptote when you get your factor doesn't cancel. There's a whole when it does. Okay, so let's take another example. F of x equals x over x squared minus 25. So what does this equal? Well, x squared minus 25 is a difference of squares. It's x plus 5 times x minus 5. The denominator equals 0. At x equals negative 5 and at x equals 5. Both of these are vertical asymptotes. Because nothing cancels. If something had canceled, we would have had a whole. Let's take one last one. You're essentially just finding the domain of the function here. Let's say that we have f of x equals x squared minus 5x minus 6 over x squared minus 1. You're factoring. You have to factor everything because you need to know if something cancels. Numerator factors to x minus 6 times x plus 1. Denominator is a difference of squares. The x plus 1 cancels. So what does this tell us? The vertical asymptote, there is a vertical asymptote at x equals 1. There is a hole at x equals negative 1. Okay, this is because x plus 1 cancels. Okay, x minus 1 doesn't cancel, so therefore it's a vertical asymptote. Okay. Always factor first. And you need to factor everything. So to find the vertical asymptotes and the holes, you need to find where the denominator equals 0. You're looking at the domain. If it's a factor that cancels, it's a hole. If it's a factor that doesn't cancel, it's a vertical asymptote. That's it. Okay. In the next video, we'll talk about horizontal asymptotes.